Hey everyone! In this video we're going to talk about writing and balancing chemical equations. So chemical equations are very important because they describe chemical reactions. And chemical reactions are the processes by which certain substances get converted into new substances. So for instance, this chemical equation up here describes the reaction known as photosynthesis. So photosynthesis is the process by which plants take in sunlight and they use it to convert carbon dioxide and water into oxygen and glucose. This is a very important chemical reaction that takes place inside of plants. And then this chemical equation down here describes the production of sulfuric acid from sulfur dioxide. So sulfur dioxide is a very common pollutant. And what it does is it reacts with oxygen and water in the air to produce sulfuric acid. And when you get enough sulfuric acid, it'll accumulate and it'll fall down in the form of acid rain. And this can be very harmful to plants and aquatic life. So there's two examples of chemical equations, and then I have one more example for you before we move on, and that is the combination of hydrogen and oxygen to form water, which is the chemical reaction that actually takes place inside of fuel cells. So not only does this reaction give off energy, but it's also very clean because the only byproduct of the reaction is water. So this could be a very valuable and important alternative energy source someday. So let's go ahead and get into the nuts and bolts of chemical equations. So this example right here is actually an equation that describes the combustion of propane. So propane, C3H8, is going to react with oxygen, and that's going to form carbon dioxide and water. And this is actually the chemical reaction that takes place inside of your gas grill. So anytime you fire up your gas grill, this chemical equation is describing the reaction that's going on. Now, the substances on the left-hand side of the equation, so in this case that would be propane and oxygen, these are called the reactants. So these are the substances that react together to form the substances on the right-hand side of the equation, which we call the products. And these little italicized letters in parentheses here, we call these the states of the reactants and products. And there are four main states that we show in chemical equations, and they are gas, which is represented by a G, liquid, which is represented by an L, solid, which is represented by an S, and aqueous, which is represented by AQ. Aqueous means that whatever substance you have is dissolved in water. So you have a water solution of your reactant or product. Now, one thing should be noticeably wrong with this chemical equation here. You can see that we have 8 hydrogen atoms on the left-hand side of the equation, but only 2 on the right-hand side of the equation. And we can also see that we have 2 oxygen atoms on the left-hand side of the equation, and then 3 oxygen atoms on the right-hand side. 2 from CO2 and then 1 from H2O. So it looks like we have destroyed hydrogen and we've also created oxygen, and according to the law of conservation of mass, this is a big no-no. You can't do that. Remember, matter can neither be created nor destroyed in a chemical reaction. So what we need to do is we need to modify this equation to avoid violating the law of conservation of mass. And the way that we do that is we assign these numbers here on the reactants or products, and we call these numbers coefficients. So what the coefficients do is they allow us to balance the chemical equation so that the atoms of each element are equal on the left-hand side and on the right-hand side of the equation. So what we've done with these coefficients is we haven't changed the type of atoms or molecules. Instead, what we've done is we've changed the number of atoms or molecules in the chemical equation. So this gives us a better feel for what's going on, and we can look at this visually and we can see exactly what we start with and what we end with. So that, according to this balanced chemical equation here, we have 1 molecule of propane, which is C3H8. And now it may look like there's fewer than 8 hydrogens in this propane molecule. There are 8 hydrogens, but you just can't see them all. Some of them are sort of eclipsed by those carbon atoms. And then also on the left-hand side of the equation, we have 5 oxygen molecules, 5 O2s. And then on the right-hand side, we have 3 CO2 molecules and 4 water molecules. And I would certainly encourage you to pause this video and count the number of carbons, the number of hydrogens, and the number of oxygens on each side so you can confirm for yourself that they are indeed equal. So how did we come up with these coefficients? I mean, I already had them written down in this example, but how do we balance a chemical equation? So I'm going to give you a couple of tips on balancing chemical equations. Most people I think they just do it kind of by a trial and error process, but there actually is a systematic method that can actually lead you to the correct balanced chemical equation every single time. So I'd like to share that with you now. So what you want to do is, first of all, you want to balance one element at a time. So you don't want to balance more than one element at a time because that might sort of overwhelm you a little bit, and it's not really necessary. All you have to do is just balance one element at a time. Also, what you want to do is you want to start with an element that appears only once on either side of the equation. So I'm going to elaborate on that a little bit more in the example that I've chosen. Thirdly, you want to keep a running count of all of your atoms. So every time you assign a coefficient, what you're doing is you're changing the number of atoms of certain elements, either on your left-hand side or your right-hand side. So you want to keep count with every coefficient that you assign of how many atoms of every single element that you have. And then lastly, if you end up with a fractional coefficient, so in other words, if you end up with a coefficient that is a fraction instead of a whole number, don't panic, don't start all over. Instead, what you can do is you can keep that fractional coefficient, and then what you can do is you can multiply all of your coefficients by the denominator of that fraction, and that's going to give you the balanced chemical equation with whole numbers all around. So that may have sounded confusing, but in the example that I've chosen, we are going to end up with a fractional coefficient, so I will definitely elaborate on that very shortly. So let's go ahead and see if we can't balance a chemical equation. So this chemical equation describes the combustion reaction of a compound called octane, which is C8H18. And notice that we have, I've set up my little table here where I have a reactants column and a products column, and then I have rows corresponding to each element, carbon, hydrogen, and oxygen, which are the only three elements in this equation. So what I'm going to do, the way I like to do these is I like to start by assigning coefficients of 0 to everything. So that means that we have zero atoms of all of the elements in this chemical reaction. So now what we have to do is we have to choose an element that we got to start with. And in this case, we could start with carbon or we could start with hydrogen, but we wouldn't want to start with oxygen because oxygen actually appears twice on the right-hand side of the equation. We see that there is oxygen in CO2 and there's also oxygen in H2O. So what we're going to do is we're going to start with either carbon or hydrogen, and then we're going to save oxygen for last. So I have arbitrarily here decided to start with carbon. So now what I'm going to do is I'm going to identify which carbon-containing compound has the most carbon atoms. So we need to compare them. There's octane, which has 8 carbon atoms, and then on the right-hand side there's CO2, which has only 1 carbon atom. So I'm going to start with octane, and I'm going to give it a coefficient of 1. Now, since I've given octane a coefficient of 1, I've actually changed the number of carbon atoms and hydrogen atoms on the left-hand side of the equation. So I now have 8 carbon atoms and 18 hydrogen atoms. So since I'm starting with carbon, what I need to do is I need to balance carbon by assigning a coefficient on CO2 that's going to give me 8 carbon atoms. And that coefficient, of course, is 8. And since I've given a coefficient of 8 to the CO2, I've changed the number of carbons and the number of oxygens on the right-hand side of the equation. So I now have 8 carbon atoms and 16 oxygen atoms on the right-hand side of the equation. And look at that, we've just balanced carbon. It's very simple. So what we're going to do now is we're going to move on to hydrogen. Like I said, we're going to save oxygen for last. So what we need to do is notice that we have 18 hydrogen atoms on the left-hand side of the equation. So I need to figure out a coefficient to put in front of the water that's going to give us 18 hydrogen atoms on the right. So since there are 2 hydrogen atoms per water molecule, I need to assign a coefficient that when multiplied by 2 is going to give us 18. So what times 2 equals 18? That would be 9. So that's the coefficient that I'm going to go with. So that gives us 18 hydrogen atoms, but it also changes the number of oxygen atoms that we have. So before we had 16 oxygen atoms on the right-hand side of the equation. Now we have an additional 9 oxygen atoms on the right-hand side. So that's going to bring up the number of oxygen atoms to 25. So that's 16 coming from the CO2 and then 9 coming from the H2O. Add those together and you get 25. So now we have successfully balanced hydrogen. So now we have to move on to the oxygen. So we've saved the trickiest for last. So notice that we have 25 oxygens on the right-hand side of the equation. So now we need 25 oxygens on the left-hand side of the equation. But there's a problem here, and the problem is that each O2 has 2 oxygen atoms. So we need to find a number that when we multiply it by 2 is going to give us 25. Now if we go with 12 times 2 is 24, then we'll have too few oxygens. And then if we use 13, that's going to give us 13 times 2, which is 26, and then we'll have too many oxygens. So we can see in this case we're going to end up with a fractional coefficient. So we need to figure out a coefficient that when multiplied by 2 is going to give us 25. So in other words, I'll just set up an equation like this. I'll just say x times 2 equals 25. So now in this case all we have to do is just solve for x. We can do so by dividing both sides by 2, and that's going to give us x equals 25 halves. So 25 over 2 is my coefficient that I'm going to put in front of the oxygen. So notice that 25 halves times 2, that's going to give us 25 oxygens. So now we have balanced all 3 of the elements, but we're not quite finished because what we have to do is we can't leave the fractional coefficient there. We have to use whole numbers all around. So what we're going to do is we're going to multiply by the denominator of that fraction. Like I said earlier, we're going to multiply by this 2, or excuse me, we're going to multiply this 2 by our entire equation, and that's going to change all of our coefficients. So again, we're going to multiply that whole equation by 2. That's going to change the coefficient in front of octane to 2. 1 times 2 is 2. That's going to change the coefficient in front of the O2 to 25. That's going to change the coefficient of carbon dioxide into 16. 8 times 2 is 16. And then lastly, our coefficient in front of water is going to be 9 times 2, which is 18. So this is our balanced chemical equation. And now that we've multiplied the equation by 2, now we can multiply all of our atoms by 2. So that's going to give us 16 carbons on each side. It's going to give us 36 hydrogens on each side. And then it's also going to give us 50 oxygens on each side. So again, there was nothing tricky here. It was a very systematic approach. We started with carbon, and then we saved oxygen for last. We only balanced one element at a time. We kept a running count of all of our elements. And then since we ended up with a fractional coefficient, we didn't have to, like I said, we didn't have to panic, we didn't have to start all over. All we did was we just kept that fractional coefficient, but then multiplied the entire equation by the denominator of the fraction. So there you go. There is how to balance chemical equations. I only went over one example in this video, but if you'd like to see more examples, go ahead and put a comment on this video. If I get enough comments asking for some more examples, then I'll be compelled to make another video on it. So I hope this was helpful to you guys, and all right, take it easy.